Hejsan allihopa och vart välkomna ska ni vara till dagens event här på Gate 10. Innan vi drar igång så vill jag passa på att berätta lite om Gate 10 för alla er som är nya medlemmar har idag. Gate 10 är en kostnadsfri mötesplats som drivs av Internetstiftelsen. Internetstiftelsen är en oberoende organisation som verkar för ett internet som bidrar positivt till människan och samhället. Communityt här på Gate 10 bygger på att våra medlemmar stöttar varandra och delar med sig av sina erfarenheter för att växa och utvecklas tillsammans. Här på Gate 10 kan du delta i event som skapar av andra fantastiska medlemmar, precis som du gör idag. Men du kan också sitta här och jobba i vår arbetslunch. Du kan spela in poddar, du kan använda våra 3D-skrivare eller så kan du anordna ett eget event om du vill. Och allt det här är helt kostnadsfritt. Jag hoppas att dagens event blir värdefullt för dig. Om du vill dela med dig av din kunskap eller har några frågor, kontakta oss gärna på Gate 10.
A bit further. Good afternoon, everyone. My name is Jasim Abbassi and I am a software developer at Syntronic. My area of specialization is machine learning, AI and autonomous driving. I hold a dual master degree, one in robotics and control engineering from Umeå University and another is in data science from the Luleå University. I am working on a AI driven software solution for autonomous driving here in Syntronic. The topic of my presentation is AI driven data solution for autonomous vehicle. Today the agenda of presentation is that we will briefly discuss about the importance of data in machine learning and AI, and then I will describe about the life cycle of data in machine learning, and we will also discuss about the data collection, our own custom design data collection pipeline. And we have also developed our data logger tool. We can talk about also briefly about this, and then data pre-processing, and at the end we will discuss. So we have a Q&A question and answer session. If you have any question, then we will discuss it at the end. Why we need data for machine learning? Data is the fundamental element in the development of machine learning model. It is a critical component to determine the performance of ML model. ML model use data to learn pattern and relationship between input and output variable. Later they can use for classification and prediction. Bad and unreliable data can be lead to a unreliable model. The quality of data directly impact the model performance. The good quality of data enhance the model robustness and generalization. Bad quality may result in bad predictions and bad classifications. In ML model, data is the heart of every model's success. In order to work with the data, it is ensures that it must follow a life cycle. The purpose of data life cycle is that it shows that it will give us the good result and good predictions and good solutions, whatever purpose we have developed this. It consists of, normally it consists of like number of steps. At the beginning, it start with the data collection. First step is that data collection. We will collect the data from different source. In our case, in case of autonomous driving, this data is collecting from different source like sensor, like cameras, lidar, radars, and different sensors, IMUs. Once we collect the data, then next step is the pre-processing. In pre-processing, data collecting from the sensor is lot of buggy data. There may be not correct, there is some missing values. We need to be figuring out that. Sometimes the junk data or missing data come into the data collection, data storage. We need to be clean before that it will train the model. For example, in case of IMU data, when we use like X values, sometimes we get missing values like NaN values, duplicate values. We need to be clean it before training the model. There is a lot of different pre-processing steps that involve for this, and I will discuss later in each steps that involve in pre-process steps. Once we collect the data, then we train the model. If we work with like image, video, and this stuff, then we need to look into which model we are going to use for classification, prediction, whether we work with the time series data, whether which predictive model we are going to use. After training, we need to look into it that how we can validate our model for giving them new data, test data. Validation is very important, that sometimes only training data is providing and the model is performing well, but when we validate the model, it may be not good as what we are expecting on it. And at the end, we will evaluate the test the model performance on unseen data or new data, also like validation and evaluation. Normally, data is categorized in 3 different categories: structured data, unstructured data, and semi-structured data. In structured data, we have got very good data in tabular form, and it's mostly very well organized. For example, in case of like GPS, we will store the GPS coordinates and information in tabular form, and this is quite easy to store and maintain on it. And most of the data what we will daily face is like unstructured data. In unstructured data is mostly come from like camera, videos, different sensors. They are quite unstructured in nature, and it's quite difficult to save it like a tabular form and these things. And they also take a lot of storage and things, and mostly IoT devices and this one. And in case of unstructured data is lidar. In case of autonomous driving, we get this unstructured data from lidar, radar, and cameras, and from different cameras for autonomous driving. And semi-structured data is partially organized but lack a fixed schema, like as in structured data, and it may be in JSON format, Excel log files from CAN bus from the vehicle. We get this structure, some semi-structured data. Where does all this data come from in case of autonomous driving? The data come from the different source. As you can see that each color represent different type of sensors: camera, long range radar, short medium range, ultrasonic, and lidar. These are the different source we collect the data from autonomous driving. Camera is used, for example, different type of object recognition, detections, traffic sign detections, and all these things. And long range radar is used to control the speed from the long distance, and short medium range lidar is used to detect the blind spot detections and rear hazard alerts and cross traffic alerts. These and ultrasonic is mostly used for like close detection for parking assistance and this stuff. And lidar is also used for detections, but the advantage of lidar is also simultaneous use for mapping and 3D mapping of the environment as well. There are different sources of collecting the data from autonomous driving. Currently, there are a lot of simulator available for collecting the autonomous driving data, like CARLA, Audacity, AirSim. We have collecting most of data is the CARLA. The reason for using the CARLA is that it provides a realistic environment to test the autonomous driving algorithm in a diverse driving scenarios as well. And it's also provide a risk-free testing ground, and it can support like multiple cameras like LiDAR, radar, segmentation camera. There are variety of sensors and camera available in CARLA, and it's also ideal for early stage algorithm testing. Here you can see that we have developed in-house, and it's also provide a custom integration of map. For example, if you want to test your own different driving scenarios, this is the map we have created, in-house created and developed and integrated with the CARLA, and this is the vehicle we have also created and integrate it with the CARLA simulator. And the good thing about CARLA is that you can also provide and control the vehicle dynamics, and it's provide lot of customizations. We not only use this only particular map, they have like more than like 12 to 16 different maps based on different cities and different environment, different conditions. And another advantage of using CARLA is that you can also control the weather in it, for example like snow, rainy, fog and all these things. So it will provide quite realistic environment to test your algorithm in this simulator. And after we have tested the algorithm in CARLA simulator, we have also a physical track in our in-house here in Syntronic, where you can test the train algorithm, a train model, a train on the physical track as well. We have same like the car which you have shown in the simulating environment. We have also a physical car here in this in our in-house, where we can validate this algorithm on the physical track also. The purpose of testing this thing is that it provide it bridge the gap between like simulator and reality. We can easily test our algorithm this quite on the physical track also, and because we have this small car and we test everything in-house from both in simulator and validate it on the physical track. There is a diverse data source for autonomous driving where you can collect and download the data. There is public data sets that is mostly available like ET, Vermo, data source, and these are the public data sets that is free to access, and you can download and test on it your machine learning and AI algorithms. But there is also a crowdsourced data set that is OpenStreetCam, AI, and these are also crowd data source where you can use different type of LiDAR data, camera data, and most of these are also for annotated data, and some of them are only for few cities. They cover only few diverse driving scenarios, and some of them are quite good and there are multiple weather conditions and different data sets available in it. In-house we have developed here in Syntronic like 3 different type of pipelines that will collect the autonomous data from simulator and on physical track. We call it, this pipeline is norm flow, spin flow and main flow. There is a different purpose and for each pipeline, and they will serve as a different way of data collections. We will briefly cover on this. In non-flow and spin flow is they autonomously navigate into the CARLA map and collect the data autonomously, and main flow is likely human-driven data collection methods. These both methods we can collect the data from both simulator and real world. a real world. In our case is like a physical track, but for we collect data for our autonomous driving, not only for this particular physical track. We use different CARLA map for applying different diverse weather conditions and collect this data for our autonomous and vision based navigations. Here in first our pipeline we have developed for that will collect the data autonomously is called NERM flow pipeline. In NERM flow pipeline, at the beginning car is get the initial and randomly select the initial goal and the target final goal where we were initial point and the target point where they want to go, and then they generate the path from starting to the goal position and autonomously navigating from the start to goal position. And at the same time they will collect the data from like RGB camera, segmentation camera data, IMU data, vehicle throttle information, and GPS information. This data we will use to build different type of model later, for example object detection, classification and predictive model. The drawback, there is certain positive thing about this, that because in most of the cases in CARLA in this we have very less, like for example like quite few turns straight and left turns, and this as you can see that this here in this graph you can see like majority of data with this pipeline we will get like a straight behavior, and there is like very less information about left turn, right turn, because the data we have collecting is like autonomously, and car is driving with the different towns and different cities and different one, but the distribution of data is very less for left turn and right turn. When we going to build the model in machine learning and AI, our car start learning straight behavior, bias to the straight behavior instead of left and right turn. And another is and they have challenging in learning for left and right turn. To overcome this problem, we have created another pipeline that is we call it spin flow pipeline. In spin flow pipeline, our car is as same get the starting and goal position, but instead of going directly there, in each point they randomly shift between 15 to 25 degree and take the picture of the environment and then move along with the steering value, throttle information, GPS and IMU data, and then go from start to goal position. In this case we can increase the diversity of the data in our data sets. They will also this pipeline also will work like autonomously. There is no human or man involvement on it, and we have attached in both in our pipeline is like if for example if collision is happen or something uncertain things happen on this, then they automatically stop data collection method. So we make sure that there is no bias or collision or incorrect data goes into our data repository. And they will provide we will get easily get most of left and right turn, because another thing is that in this case we will use randomly shift. We are not specifying only particular angle between that, so we are not biased for specific angle that only shift in that particular angle. We will randomly shift from 15 to 25 degrees, so that car will automatically take data and take samples from that angle, that range. The problem with this is that in this case our car is driving very slowly as compared to previous pipeline, and it takes its resource incentive. It takes so long time to collect data. Is very slow, but we get quite diverse set of data range from different scenarios and different conditions. And it's also with this, then there is also a concern of overfitting concern from left and right turn, and this. To overcome all this problem, we have also developed another pipeline that is called main flow pipeline. In main flow pipeline, it is different with the previous two pipeline is that in previous two pipeline we drive the car autonomously. In this pipeline we keep the human in the loop, so that we get to integrate the human functionality in the data also, so that when we train the model we have different driving sets, both on AI based and also in like a human. And when we collect this data from main flow pipeline, this only for we get data from different human driving on it. We learn the behavior of data from both physical track and the simulated environment, and we save on this data, and that later we can use this data for the prediction of our model and these things. And the drawback of this approach is that they may be prone for the human error. For example, someone doing bad driving or bad way of doing driving, then maybe we get that type of data also in these things. But they are also time consuming for each human. They go and collect this data and this. The data we collect from the CARLA and this one is that there is different type of RGB and segmentation data. In RGB data we will use this for object detection and recognition system for this one. And here we have similar image for in case segmentation camera. As you can see, the car is assigning one particular color in it, and road is assigning to the specific color, because each pixel is annotated based on the predefined class on it, and it's quite good for building like a steering control and vision application around on it. But RGB data is also very important. For example, if you work with the traffic light, road sign detection and these things, then you can easily detect with these things. But here in case of segmentation camera, you will each traffic light assign one color. Then it will be quite difficult for you for the model to differentiate between the different color on it. But for example, in segmentation camera, we use this for our steering control and these things. The data for in this case we have contain around like 180k images along with steering values, IM data and all these things, both for RGB and segmentation along with sensor information, throttle information, all these things. As you can see, both have containing the same size of data, but the data which we have collected, this one, you see the RGB data take more space into your local storage, and then same type of data without any compression in both cases, they take quite less time. It means that, for example, if we train the model based on this RGB data and segmentation data, then our model become quite easily trained on. They have computationally less expensive segmentation data as compared to the RGB data, and they take much less space in storage. And this, there is certain advantage on it for this one. For this RGB camera, as I mentioned, we can use for object detection, recognition, traffic light. If you try to figuring out that particular object in your scene, for example, if you want to detect the vehicle and with vehicle category and want to calculate that to which type of vehicle go past in that particular road, then you will rely on this RGB data, because in case of segmentation data you will get same type of color and same type of information on it, and then you use these things for but for steering control and throttle information. And it's quite easy for the car and quite easy for a deep learning model to only focus on learn on this model that driving road they have singular, and then quite easily they navigate between road and the path and all these things. In-house we have developed also another tool that is we called it data logger tool, that is also easily integrate with the ROS robot operating system. The purpose of this creating this tool is that we get all the data information on the dashboard like style this one, and here is quite easy to use. Simply where you can just user can specify the path where they want to store the data, and they have visually control of start recording and stop recording. And here it also shows the driving mode. The data we have collected in is divided into 4 different driving mode. We are divided on it, like 30 km/h we called it the slow mode, and like normal mode 60 km/h, 80 km like a fast mode, and 100 km/h like a ego mode. The purpose of dividing this different categories of this one is, for example, when user try to give maximum throttle in slow mode, they will maximum go with the 30 km/h speeds. The purpose of this one is that when we train the model, then we need to know that which area our car is lacking the learning behavior and which area they are very good in it, and then we will only need to focus on that. For example, if the car is very good in slow mode, then we don't need to collect the data from the slow mode. Then simply select the mode that we want to collect in a normal mode, slow mode, and different mode. For highways, we use like a quite high speed like ego vehicle, and we select that particular map, and then we go with that particular map. And then based on that, when we create our data sets for this one, is that then we create diversity of data sets, that how many samples we collect from this cluster. We can collect this type of cluster and this type of cluster. Then we combine these, then we get quite diverse data set from different driving condition in this. And they will provide the real-time updates. And for example, in this case, they also show the status that whether you are currently recording the data or not recording the data. And then here they will show you the total number of samples that currently you have collected for this particular mode, and you don't need to look into it or visually make the graph and see that. For example, we are divided like straight driving, right turn and left turn, anything around like particular range. Let's suppose less than minus 0.4 to this one we say left turn, positive plus 4 to this one we say right turn, and then between this one we call it straight turn. And then we get live data, how many samples we have collected on it. And then here you will easily look into it that whether the data set we are collecting on is like a balanced data or imbalanced data. Then user don't need to be look into it like plotting and then figuring out that whether data is placed or not, and which type, how many samples we have collected on this. This is very good for those who are working with like machine learning, building vision based application, their project. Here next step is very important. When we collect the data, then next important step is that data pre-processing. Data pre-processing is the heart of machine learning in AI model. Most of people just assume that we just collect the data and put the AI model and then we get the result on it. In reality, there is a lot of steps behind on it, that each data is not goes into the machine learning and AI model. We need to be data clean on it. The data cleaning is that we need to check that, for example, in case of numerical data, we will check on it that whether they have any missing values in the data sets. Sometimes the data is based on time series data. The data is relevant from the previous steps on it. Then you need to fill on it. Then you will, there is a different method. For example, you would just take the mean and variance, mean and median and integrate. But there is the more advanced way that you can use unsupervised machine learning and predict that value based on this data, and then fill on data before sending to the machine learning and AI model on it. And once data in, and next step is that normalization. Normalization is also very important. It's because it will make model to learn fast behavior. For example, in case of image data, we can normalize it value between 0 and 1, for example, divided by 255, and there is a lot of normalization techniques involved on it. This is very simple techniques we can use most of cases, is that so that when we provide this data to the neural network, a deep neural network, and it's quite easy for a model to learn between 0 and 1 the value. If there is any big peaks in the data sets, it's quite easy to learn. And the next important step is the feature engineering. In feature engineering, we need to select that which type of feature for building a machine learning model to use for a prediction on it. That is very important data. That is very important part of any machine learning model, and success of machine learning model is based on this feature, which type of feature we are going to extract on it. for example, if we are working with like some applications, we have given like 5 different features, and we train the data on it, and then we get the data with based on prediction, and when we analysis on it in the based on feature, we say that feature 1, 3 and 5 are 90% contributing in the prediction model. Then we will try to remove that feature that is not necessarily we put into the model, make it over complex for prediction and this stuff. And then also scaling is used, for example, like to compare data from different let's suppose we have like working with like data for healthcare, a medical application, like someone have age and then salary, and then we compare on it based on some standard that we can compare based on age and scaling in specific range, not like quite big difference in plotting and these things. And then data exploration is like that. After that, we will analysis on data, which type of feature and all these things we will need to figuring out the required settings or required things are match our requirement, are they fulfill our what we want to achieve or not. This is very important in case of smart future extractions. When you work with the machine learning and for autonomous driving, as you can see that we have got this data, take that image, and they have like width and height. This is 3 represent the RGB channel, red, green and blue, and then we multiply on it, we get that much feature for the one single image. And when we do build the machine learning and deep learning model around on it, as you can see that this height information is irrelevant for the ground vehicle, unless we are not making single model that will use for like a traffic light detection and these things on. Then in data pre-processing, as we mentioned, feature engineering is very important, that which information we are going to give to the machine learning and deep learning model. Here we will, when we look into it, then we make our pipeline, data pre-processing pipeline, that only extract the road information, not like a height information. And when we think of road information, this corner information is very important to that should be in the road. It's quite easy for a model to learn that what, and we are not giving them unnecessary feature into that model. And here, as you can see, the feature from this image to this, we have reduced 4 times less feature as compared to this one, and it means that we can computationally less expensive in this model as compared to this model. And we were giving like lot of biased data to the model for training these things, because we are giving unnecessary features to the model only. These are some pre-processing and some visual things for we need to be considered when we building machine learning and deep learning model. Another interesting techniques for example, if you are working with the machine learning and deep learning data and you have very less data sets, and you think that you have like building something, then you artificially increase the data training data set through data augmentation. You get one image and then you will do like flipping, scaling, noise, edge detection, lot of different things you can add on it and build the data around on it. So you will increase the diversity in the data set by data augmentations. And for our case, like in physical track, when we working with it, we collect the data in one way and then we flip on it, we get simply flip all the steering values, and this we get the data from both ways. And this is very good for changing weather condition. The advantage of this technique is that you generalize your model very well. They are not only go with one specific case for, and they will help you a lot for model generalization in this. Another thing, when you collect the data for your training data set, most of the company as the database from public and crowdsourced data set, I have mentioned that they mostly collect the data from some specific weather conditions. It is always good that when you collect the data, you need to be considered different things in it. Like for example, when you collect data, you need to consider diversity of data in it. diverse weather, sunny weather. If you work with the simulator, it's quite easy to just go with the visibility range, that how much visible things you want to train on your model. But for real track, it's quite difficult to set these parameters. Then you physically need to be drive that car in that particular condition and in that particular atmosphere. But for making to build that reliable model, you need to be consider these parameters for your model. Another important thing is that data annotation. When you labeling the data for your model in supervised learning, when you build a model, they will learn from the label that you are providing your model on it, from your ML model. If you provide the bad label, it will not. In this case, you can see that when you do data annotation, most of mistakes we can do it like we provide lot of extra information on it. We put the box quite far from it. Always think of it that when you want to detect the object, for example traffic light and these things, draw the bounding box quite precise, that there is no need to be add additional background on it. Then your model will be prone to the extra background around on it. So this is very important when you need, this is very important point when you need to be consider data annotation. So always try to avoid the adding the additional background. And sometimes another mistake, most common mistake, is that when we try to annotate the data, we will halfly label the objects. For example, if I want to then I will halfly label these objects. That is also not good idea. They will only always need to precisely label the things which you want to detect on it. Once we have data, there another significant of training, validation and test data. Training data is mostly we use for training the model. We use for training the model. But important data is also mostly people ignore is that validation data. That is very important for to tune your model parameter. And there is also a test data finally available. What is key difference between validation data and test data? When we train the model, for each epoch, for example, they will go for one training from start to go predict state, then they will tune the go with it, and then they compare your model accuracy with the validation data sets and see that whether the validation last and training last is very well or not. If the validation last is not improving after certain number of iterations, then you need to be stop the model training on it, because maybe your model is quite simple for this type, and then you need to make different model. And this is very important data set to tune your model parameters. And test data we use on it when we done the training part. For example, if we run for 100 and epochs, 103 hours of training, after that we see that the test data, the model is not performing well, then we see that, oh, we missed validation data in this thing. It is always good practice to split the data in three different sets: training data set, test data set, and validation data set. If, for example, you have very small data sets, then you will go with like 80-20 ratio, 10 ratio for test data, and 10% for validation data. But if you have like a medium sized data set, then you will go with 70% for training data set you can use, and 15% for test data, and 15% for validation data set. And if you have like a quite large amount of data, quite big data set, then it's always good that you can use 60% for training data sets, and 20% for test, and 20% for validation data set. But these are just normal, not like a standard, but normally it's good practice to use this type of things. Once we collect data, we will split the data, and then next important part is that model selections. This is very important. That, for example, if you are working with like a time series data, you need to be look into it that which type of model. For time series data, we will use reinforcement learning, recurrent neural network for time series data, and LSTM for time series data. But for most of cases, in our case, we built like machine learning, computer vision, and this stuff like images and this stuff. We mostly need a deep learning, deep neural network for multiple layers on it. The model selection is very important part. For simple model, always try to use with the simplicity simple model, then gradually increase, we go with the complex model for it. Once we select the model based on our case study, which type of, for example, in case of like image detection part, we will select that this type of deep neural network we are going to use for home. In this type of layer, hidden layer, we can use in our model, and then we train. Next step is that we can train that model based on the training set we have collected, or the training set we will have. Once we done the training, then we evaluate the performance of our model based on test data, that whether our model is performing well on the test data or not. And then if it's not performing well, then we need to tune our model. For example, tune hyperparameter, and then maybe change. So for example, if the model is performing so bad and not able to learn new things, then we need to increase the number of hidden layers in the model. And if they are working well but they are overfitting, underfitting, different scenario, we need to be figuring out that which tuning parameter we need to based on our problem. And once we done the tuning and we will get the desired result what we want to achieve, then we will finally go with the development phase, and we will simply deploy it with whether we on car or where. This is some general pipeline we have make it in our case is that raw data, then we can pre-process this data, and then we split it training and test data, and then we train on in machine learning algorithm. Then you maybe use for simple like application, you can use like random forest and this thing. For complex image and video processing and this stuff, then you will need like a convolution neural network, a deep neural network. Then based on this you can select them, then select your algorithm, and then after that you can train model. Then you can predict model scores. Like for example, in case of like image process, you use classification problem, you can use like a confusion matrix to see the model performance and this, and then evaluate on it. And you can also test on it, that in case of test data we can also use like a new and unseen data. Instead of raw data, unseen data, we will apply same like a processing pipeline what we given to the model at the beginning for training the model. For new unseen data, then they will detect based on give us the prediction exactly. Some common pitfall in this type of problem. We will mostly, most of them are, you are familiar with the underfitting problem. In high bias means that the error in the training data sets, model is not good for training, and high variance is that error in the test data sets. High bias and high variance means that our model is not performing well in both training data sets and test data sets. In this case, it means that the model we have selected for this particular problem, whether we need to change on it or whether we need to make it. For example, in case of convolution neural network, we need to increase the number of hidden layers or maybe change the different activation functions to avoid this underfitting problem. And the next thing we also face while developing this deep learning model is that overfitting problem. In overfitting case, we get this type of low bias and high variance. Low bias means that our model is very good for the training data sets but not good for the test data sets. It means that they will memorizing are familiar with the nice data set and they are not generalized well for the answer. We need to avoid this situation also. how we overcome this? Then we need to make it, for example, like regularization techniques, different regularization techniques, introduce dropout layer. They randomly drop the certain ratio of neurons in the hidden neural network while training, and then they use reconnect on it again when do the predictions on it. This way we can reduce this low by high variance to the low variance. And sometimes we need to set like a our model is overtrained on it. For example, we want to train on it like 100 epochs, 200, 300, 500. Then we need to set that early stopping criteria, that if the model is not improving, not reducing the validation loss, training loss, and this loss, then stop further training, overtune the model on it. There are a lot of different techniques. Our ultimate goal of the ML model is that we should have low bias and low variance. Means that our model should be good for training data sets, test data sets, and new unseen data sets also. So our ultimate goal should be like that. We need to be achieved these goals before deploying a model into the production. Yeah. Thank you for listening. If you have any question, you are most welcome. If
you have any questions, just sign for the mic. I'll give it to you, and you. Yeah. Here you go.
Yeah, thank you, Jasim, for a great presentation. Can you go back to the pipeline? Okay, thank you. You say the training data and the test data.
Yeah.
So if you training data, let's say, oh yeah, sorry. So if the training data is not good with the test data, so then is go back somewhere so that the training data should be the good data, and then you can test with the test data, and then go further for choosing the good train model or something like that.
Yeah, this is a general pipeline flow. We mostly, the purpose is that to show the flow of data. For example, here when we have like a raw data, then you will check data pre-processing on it, and then they split on it. For example, they have two paths on it. For example, like we have like a training data, we can train on this scenario this way up till this one and evaluate the model performance on it. Then next step is that when we train on it based on this flow, we can train our model, and when we test on it, that when we finally deploy on it, that instead of raw data we directly come from the sensor source or car, vehicle, image, and all these things. The steps we use for data pre-processing for the training, same step will be applying for the new data, whatever the image will come into our model, and they will do same like pre-processing, and then they will go this way, not like this way.
All right. Okay.
Yeah.
Okay. So you do these things in the data pre-processing.
Yes, data pre-processing.
Right.
Mostly the purpose of this way is showing that there will be just say training data sets, or test data sets, or new data sets, or unseen data sets. People name it in a different. But these steps is common for. These pre-processing steps should be applied same when we train. The step you applied for training data set, and same step will apply for the test data set.
All right. Okay.
Yeah.
Thank you.
Anyone have any?
And anybody else for questions? Yes.
Yeah, thank you for your presentation. I would like to see the slide on the different categories of data where you have unstructured data. And I'm curious about, first of all, whether the different types of data can be used in the different like procedures with like training and test and validation.
Yeah, I will go. Yes, you're talking. Yeah, There different approach will be applied for in case. For example, in structured data, let's suppose we have tabular data in rows and column form. We start with applying with different basic pre-processing steps. We will look into data in Excel sheet and see, for example, in our pipeline, see that if there is any missing values into it or not. For example, NaN value, mostly people call it NaN value. Sometimes the sensor skip that interval in that seconds on it, and then we look and we apply then pre-processing if we have large data set and they are not independent from the previous state. Then we see in our pipeline data pre-processing that remove that row where we get the NaN value. And if we are, for example, working with the stocks data or other data, that is very important from previous step, and then based on next step, time series data from previous, and then go next. Then we simply not remove that data directly from our data sets. Then we need to be filled that data with the NaN value. Then we build like unsupervised learning or simple different means different algorithm, clustering algorithm to fill that gap. And then we applied this machine learning and deep learning further supervised learning techniques on it in case of structured data. In case of unstructured data, as mostly we talk about a lot of things like image, different type of feature, what we want to go on it, and then what type of feature we need on it. Then we look into structured. Sometimes you can also face some situation that you need to give the image data along with the numerical data into the model. Then you need to different deep processing pipeline that will handling the numerical data, once that will handling the imaging data, what type of feature you are going to give to the model on it. For example, in case of autonomous driving, you will build a vision-based system, and car is going from start to goal position. You will give the model like a image data along with the GPS information that is in like Excel and tabular form and these things. Then you will give this feature and this feature, and then you will build the model around.
As a follow-up, I'm curious about whether the annotation is introduced as structured data along with the images.
Yeah, that is also possible. Yeah, then we can annotate on it. For example, in our case, like when we annotate on it and annotate our data like this image, and at this time the throttle value is this one and steering value is this one. When we collect the data in each scenario, they will save this data along with the throttle value and the steering value. We have numerical value. Then we need to look into it both cases the timestamp for image and the throttle value. They should be aligned with each other. It doesn't mean that if you collect the data t, for example, 1 second, then you will collect data from other only. That's why we make a data logarithm. I'll show you. Here, the tool which we have created on it, we have also set the criteria. For example, here you mentioned that we have seen left turn, right turn, and state driving. But we set that time series data information also, that they will sync with the steering value what we are saving in the CSV file. They will be sync with each other. It doesn't mean that if this steering value is t equal to 0 and we will save the image at t equal to 10. Then we will set that criteria, make sure that they will all are aligned and sync with each other. And if you annotate it in a different way, then you will get bad prediction. Car see this and you will get that steering information. I hope you understand.
Great,
yeah.
Thank you.
Great question, yeah.
And any more questions? Nope. Okay. Thank you.
Thank you for listening.